So, as you know, this assignment is a variety of applications of Faraday and Lenz's law. And Faraday's law says that you get an induced EMF in a loop or coil of wire if you have a changing magnetic flux through that wire. And so it's minus n d phi dt. So the n is the number of windings of the coil, and d phi dt is the rate at which the flux changes. And flux, of course, is the field, the area, and the cosine of the angle. And so by varying the field or the area of the coil or the angle of the coil, you can induce an EMF in a coil. And Lenz's law is the way that we get the direction. That's kind of an indication of this minus sign. The response always opposes the change. So if the flux is increasing, the induced EMF will give rise to a current, which gives rise to a field, which gives rise to a flux that opposes that increase. And if the flux is decreasing, it will oppose the decrease or try to maintain the original. So opposing the change or maintaining the original. That's Lenz's law. And here are 4 situations in which we can apply it. So let's walk through these 4 situations, and then you can answer the questions about these diagrams. So all the information is given here. It leaves nothing for you to guess at. So in figure A, the north pole of the magnet is moving into the coil. This arrow indicates that. And so the flux in this direction and the field in this direction is increasing. Since it's increasing, we have to oppose the change. We need a field and a flux in the opposite direction. And in order for that to happen, the current in the coil has to be induced in this direction that it shows by the arrow. And so if the current's in this direction, this will be the positive side of the resistor. This will be the negative side because there'll be a voltage drop across the resistor. That's what those symbols mean. So looking at it from this end, the current circulates counterclockwise. Whereas if we drop down to figure C, where the same magnet is leaving, then the field is still in this direction, but it's decreasing. It's losing field. And since it's losing field, now the induced current will produce a field to maintain the original, to keep it at its higher value. And so the current has to be in the opposite direction. Looking at it from the right side, it would be clockwise. And similarly, when you change the pole, if we bring the south pole of the magnet in, that's a field in this direction, right? Because the field lines enter the south pole. And so we're getting a field and an increasing field along the x-axis. Since it's increasing, the induced EMF, the induced current, the induced field has to be in the opposite direction. And so we get current that's going clockwise, looked at from the right side. And when we go to the opposite, pulling the south pole out, we get the opposite direction of putting it in, and we get the opposite direction of pulling a north pole out. Okay, so if you can understand all this and apply it, you're in good shape as far as Lenz's law goes. Okay, this is the same as what we just did. If you drop a magnet through a conducting loop, as the magnet approaches, the field along the j hat, negative y direction, negative j hat direction is going to be increasing. And so to oppose that increase in flux, the induced current has to produce a field in the positive j hat direction. And using right-hand rule number 3, we circulate our fingers this way so that our thumb points up, because that's the direction of the field. So the induced voltage and induced current looking from above has to be counterclockwise through the loop. There's a second way that's very useful, which is kind of a corollary of Lenz's law, that helps us get the direction. I didn't talk about it in the last problem, but if the North Pole is coming in and the current is this way, then the field induced is up, and this coil, right, a current in a coil is a magnet. This becomes a dipole magnet with a field pointing up. And so as the magnet comes down, this becomes a magnet with the North Pole pointing up. And so it actually repels or slows down the falling magnet. And there's an experiment that we would normally do in lab where you drop a magnet through a copper pipe and it radically slows down the rate of falling of the magnet. So using that idea is another way of double checking when you're using Lenz's law that you're getting the right answer. Okay, 6 more applications of Lenz's law. This is the same one we just saw, right? The North Pole is approaching the coil. Flux in this direction is increasing. That will need to induce a current which is counterclockwise in order to produce a field and a flux in the opposite direction to oppose the increase or maintain the original flux. And also, if the current is counterclockwise in this direction, then the coil becomes a magnet with the North Pole facing this way, and it will oppose the motion of the magnet. If we pull the North Pole out, no surprise, it's going to be the opposite because the flux is decreasing. And so in that case, you'll want this to be the current going the opposite way so that the field is in the same direction as the field that you're losing. You're trying to maintain the original, oppose the decrease in flux. And if the current is clockwise, then this is the south pole of a magnet. And so as you try to pull the magnet away, there'll actually be an attractive force trying to hold the magnet in place. So pushing the magnet in repels the magnet. Pulling the magnet out of the coil attracts the magnet. Those are the ideas that you want to keep in mind when you do these. So in figure C, draw in the direction of the field and how it's changing. So the field lines go into the South Pole. So we have a field in this direction, and if the South Pole is moving in, we have an increasing number of field lines in this direction. So the induced current has to do what? It has to oppose the change or maintain the original, which was 0 or no flux. And so it has to, the current has to be such that it induces a field in the opposite direction. And in order to induce a field in the direction of the red arrows, the current has to circulate clockwise through the loop, looking at it from this side. Furthermore, if current is circulating clockwise, then the loop becomes a magnet with the North Pole pointing along the red field lines. This is the South Pole. We're looking at the South Pole. And so the South Pole is approaching a current loop, which is a magnet, with the opposing pole. So as you try to push the South Pole in, you'll feel resistance. Okay, see if you can do D on your own. Here the magnet is stationary and the loop is being moved toward the magnet. So see if you can come up with the answer. Okay, check your answer. So since the coil is approaching the magnet, the black field lines coming out of the North Pole will be increasing in number. So to oppose that increase in flux, the induced current has to produce a field and a flux in the opposite direction. Those are the red arrows. And in order to get a field in that direction, the current and the EMF have to be counterclockwise, looked at from this side. And a counterclockwise current going through a loop means that this front face that we're seeing is the North Pole of the magnet. So a North Pole is approaching a North Pole and you feel repulsion. So that's all consistent with Lenz's law. Clearly in the case of E, you're pulling the coil away, and so it's the reverse of D, and so everything is going to reverse. The flux will be decreasing. The induced current has to be in the opposite direction to produce a flux in the same direction to prevent the decrease in flux. And so everything will be reversed from the previous example. And in the last example, if we twist the loop this way, then that doesn't cause any change in flux, right? We're just twisting the loop. If we twisted the loop along this axis, that would be different. That would be like a motor. But since we're twisting the loop along its own circumference, it doesn't cause any change in flux. All right, you should be able to do any of these by now, I hope. So in A, the bar is sliding this way. This is a conducting rail, so the area is getting smaller, so the flux is decreasing, and the dots mean field coming out of the page. So since it's decreasing, the EMF and the current has to replace the decreasing flux. So the current's going to be clockwise, right? Because using right-hand rule number 3, if you circulate your fingers clockwise, whoops, I got it wrong. Okay, learn from your mistakes. So if you go clockwise, you'll add to the decrease, right? A field going into the page will cancel those lines coming out, and it would actually add to the decrease. So the field has to be counterclockwise, because a counterclockwise field would add field coming out of the screen, tending to prevent the decrease in flux. And this B is sliding out of, and so there's 3 dots. It's going to go to 2 dot to 1 dot. So you've got to keep the decreasing flux, and so once again it's going to be counterclockwise like A. C, is entering, so the flux is increasing. So now to prevent the increase, yes, you want to go clockwise so that you get a current which induces a field into the screen, which will tend to slow down or reduce the increasing flux. And D is also a case of increasing flux. And so once again, you're getting more and more of these field lines coming out of the page, so you got to cancel them out. You need to have a current going clockwise. And in these 2 cases, the field is changing. Nothing's moving, but if this is a magnet creating this field, if the dots are from a magnet and we reduce the current, then the field decreases. So if the field is decreasing, you want to prevent the decrease. You want to put an induced field that is in the same direction as the field you're losing, the field and flux you're losing. So that would be a counterclockwise. And for a decreasing flux, whoops, no, got it wrong. That one's wrong too, right? So here, the field is increasing, so you want to prevent the increase, so you do want to go clockwise. And if it's decreasing, you're losing dots, you're losing field lines coming out. So you need to go counterclockwise to slow down or prevent the decrease, to oppose the change or maintain the original flux. All right, number 5, here we have a conducting square loop in a magnetic field where the magnetic field is going to be changing, kind of like the last two examples, and it's going to be decreasing. So you should be familiar with this function, right? This is decaying exponential function. And so when t equals 0, e to the 0 is 1, and so the field starts at some maximum value and decays to 0. As t goes to infinity, this number goes to 0. So that is a function that we've seen before in RC circuits that does something like this, where the time constant in this case would be 1 over alpha, right? We usually wrote it as t over the time constant. And so as the field is decaying, the flux is going away. So we have field into the page. So we're losing x's, right? We're losing flux. And so the current has to be in what direction? We've got to prevent the decrease. So we want to keep the original flux. So as we lose field lines, we want to replace them. And so it's going to induce a current clockwise. Using right-hand rule number 3, a clockwise current would produce a field going into the screen, which would tend to produce the decrease. Okay, but now to actually get what the induced EMF is in this coil, we want to use Faraday's law, so we have to do some calculus. We're going to take the derivative of an exponential function, which should be pretty easy. So why don't you try and do that before you watch me do it. Okay, let's see how you did. So we want to pay attention to the math, the calculus, and the physics. So we have a changing field. The function is given to us. I kind of explained in the write-up, if the magnet producing this field in this picture were controlled by current, and if the current were coming from an RC circuit which was decaying, then the magnetic field would decay just like the current in an RC. The current and voltage in an RC circuit decays when you discharge a capacitor through a resistor. And also it's interesting to notice when you take the derivative of an exponential, you get an exponential. And physically that makes sense because the derivative is the slope. So the slope starts at 1 and goes to 0. That's exactly what this function does. And so the derivative, the exponential function, is the one function where its derivative is equal to itself. So we just take Faraday's law, E equals minus n d phi dt, where phi is BA cosine theta. And then we notice that n is 1, because it's just one loop. And we notice that the cosine of theta is equal to 0 or 180, so that's either a 1 or a negative 1. And in fact, we're not really going to worry about this negative sign because we only want to get the magnitude anyway. We're getting the direction from Lenz's law. But anyway, I left the negative sign, and so we have the cosine of theta is 1. A is a constant, it comes out, and we just take the derivative of b with respect to t. This is the function b, and so when we take the derivative of this function with respect to t, the b naught, that should be a b naught. The b naught comes out, and because it's a constant, and then when we take the derivative, the coefficient of the variable t comes out, the negative alpha, and then the derivative is the exponential itself, and so I just cancel these negative signs, but again, we're not worried about the negative sign, so we have 3 constants, and an exponential function, which means that as the field decays towards 0, the induced EMF is going to decay to 0. And why is that? Because the rate of change is high here, so the induced EMF will be high because it depends on the derivative, the rate of change. And the rate of change here is 0. So toward the end, the field isn't changing, the flux isn't changing, and the EMF will not be, there'll be no EMF, it'll be 0. The equations show you current, so to get the current, you take, remember, EMF is the induced voltage. So we just divide the voltage by the resistance to get the current. And the current will start at some maximum value, which depends on these 4 constants, and then it will decay to 0 over time according to this exponential factor. So you do have to put the numbers in there and do the calculations and find the right symbolic equations and the right numerical equations. I'll leave that part up to you. Okay, number 6 is just an extension of number 5, and number 9 needs to be done before number 7, so let's do number 8. And this is something that we do in lab, but we're not in lab. We take a coin, like a large metal coin, it could be a silver dollar or a quarter, and you balance it on the edge, and it's metal, so it's a conductor, and the coins are non-magnetic materials, right? Coins are made out of non-magnetic material. I have some aluminum coins that we use. And so if you put the magnet next to a piece of aluminum or any coin except for a nickel, it won't attract to the magnet at all because it has no iron in it. So if you balance the coin and hold the magnet stationary, the coin won't move. But if you move the magnet toward the coin, what you find out is that the coin falls backwards. Or if you balance the coin and hold the magnet close to it stationary and then pull it away quickly, the coin will fall toward the magnet. And so this is something we've talked about before. So think of the coin. If I'm moving the magnet toward the thing, then there's an increasing flux through the metal. That's going to induce an EMF, which tends to oppose the change. And so the current, as the North Pole is approaching, we're getting increasing flux lines this way. And so we have to induce a current, which gives us a field in the opposite direction. And that would be a current that would circulate this way around the coin using right-hand rule number 3. You would get this induced field and flux would tend to prevent the increase. And that means that the coin becomes a magnet, and this is the North Pole. So as you approach it, this becomes a magnet with the North Pole, and the magnet repels the coin and knocks it over. And by the same argument, when you pull it away, you're reducing the flux or field in this direction. So now you're going to induce a current in the opposite direction, which will produce a field this way to prevent the decreasing flux. That makes this a south pole, and so when you pull it away, the coin is attracted to the magnet and falls toward the magnet. So this is something that you all would have gotten to do in lab, but unfortunately you weren't able to because of our remote learning status. Number 9, there's a lot of physics embedded in this problem. So let's go through some of it and then we can talk about answering the questions. So you have 2 conducting rails connected by a resistor, so this forms a conducting circuit, and as the bar slides, the flux is going to increase. So the induced current and EMF has to produce a field which opposes the increase or maintains the original. So that means that the current has to be clockwise, because, nope, I said it wrong. Has to be counterclockwise, because as the bar slides, using right-hand rule number 3, if you circulate your fingers counterclockwise, your thumb comes out of the screen. And so the field coming out of the screen will tend to prevent or oppose the increasing flux. And that EMF that's induced can be found this way, but there's a simple equation on your equation sheet. But let's derive it. Try and derive it. Use this to derive the result, which is on your equation sheet, which says E for this situation is BLV. So see if you can derive that from Faraday's law. Okay, Faraday's law, E equals minus n d phi, which is BA cosine theta dt. N is 1, right? There's just one loop. And B is constant. The field doesn't vary, so that comes out. And the cosine is 1 because the field is in the plane, is perpendicular to the screen, and the normal vector to the area, right? That's how we indicate the direction of the area. So they're parallel. The angle is 0 degrees. So that's 1. That's 1. So we just get E equals B times dA dt, but A is the length of the bar times the width of the rails. But the length of the bar is constant, so that comes out. And so the only thing that's changing is, as the bar slides, the width of the rectangle changes. And the rate at which the width changes over time, I think it's obvious, is simply the velocity. So there's your E equals BLV for this type of situation. That's on your equation sheet, but you should be able to derive it. Now, the other thing to notice is we can actually, independent of Faraday and Lenz, if we take a wire and move it through a magnetic field, then the charges, let's imagine free positive charges in the wire, are moving this way. And if we use right-hand rule number 1, we point our finger along the direction of the direction that the charge is moving in, the velocity vector. The field is into the page, and you see that there's a force down. And so if the force on the charges is down, that means the current is going to circulate this way, counterclockwise, which is what we said earlier. So even independent of Faraday's law, we can figure that out. However, now once the current starts flowing, we have current going in this direction in a magnetic field. So think about it. That's right-hand rule number 1, right? Go back to week 9. The force on a current carrying wire is ILB. So the current's going down, and the field is into the board. So if you use right-hand rule number 1, put your finger down, your index finger down, your middle finger into the page, and that says that the force on this wire is going to be in this direction, right? It's a current carrying wire in a magnetic field. So there's a force opposing the motion of the wire. So what does that mean? That means as you try to slide the wire this way, there's a force opposing that way. And so you have to apply a force which is equal and opposite to this force, this ILB, in order to make the wire slide at a constant velocity. So constant velocity means the sum of the forces is 0. So that means you need an applied force, which is equal and opposite to the magnetic force on the wire in this direction in order to make it slide at a constant speed. And so that's all the physics that you're going to have to use when you do this problem. I think the rest of it is just getting the numbers right, and I think you can do that. Okay, problem 7, which is really an extension of number 9. They should be reversed in their order, but anyway. So in this case, we have 2 sliding bars. So as the bar slides this way, the flux is increasing. And so by Lenz's law, we get a counterclockwise EMF and current using right-hand rule number 3, producing a field coming out of the screen to tend to prevent the increase. By the same logic, you're going to get a counterclockwise current in this loop, because that's also an increasing flux over here as the rod slides this way. Okay, so look at the problem, read it, and redraw this diagram and label it with all the information you need to solve the problem, and then come back. So this is what I did. I indicated that the 2 bars are resistors. I put down what their resistance was and how they're labeled from the information given. This is called resistor 3. This is called resistor 2. I indicated that they are resistors. I wrote in what the velocity of the 2 bars is. And then I also indicated the current. So notice there are 2 sliding bars, so 2 sources of EMF. And so each sliding bar, you can picture it like a battery. Let me do that. There we go. I put in a battery symbol. Why? Because the current's going counterclockwise, so I face the battery this way. And this current is going counterclockwise, so I face the battery that way. Remember, it's not really a battery, it's an induced EMF, but just to give us a picture. And so what we have is a circuit with 3 currents. I1 is going this way, I2 is going that way. You kind of have to guess which way I3 is going to go, because we don't know which one is bigger. And this one's coming out of the junction, this one's going into the junction. So assuming I2 is bigger, I put I3 that way. I'm guessing. And so this is a Kirchhoff current rule, voltage rule circuit. So you have to write 3 equations with 3 unknowns and solve it. Ugh, I know those are tedious, but let's try. So let's do this junction and this loop and this loop. So that's the 3 equations. Why don't you try writing those 3 equations and then come back and check. So here are your 3 equations. If you go to this junction, I2 goes in and I1 and I3 come out. So there's our junction rule or current rule equation. And then we need the 2 voltage, sum the voltages. So if I start here at this imaginary battery, that's the induced EMF. So that's BLV1 for this circuit in this direction. And since I go in this direction, I'm going opposite the direction of I3, so I have to make that positive. Remember how to do the Kirchhoff rule, I3, R3 positive. But I go in the direction of the current through resistor 1, and so that's negative. And then when I do this loop, I start here and I get a positive BLV2 for the induced EMF here. And then since I go in the direction of I2, I get a negative I2R2. And then in the direction of I3 is going, I get a negative I3R3. Those equations are both equal to 0. And so these are the 3 equations that you have to solve to get the currents in the circuit. The hard part is that algebra. Whoops, I just noticed that I give you the currents, which is good because the algebra of solving these three equations is quite tedious and prone to mistakes. And also I noticed that I label this in the multiple choice question as being the induced voltage on that through that first resistor. So this BLV is the way that you get V1, and I think you've done that calculation already. And so this would be what I'm calling voltage 2, the induced voltage in the right-hand loop. And finally, recall from the previous problem that when a wire is moving in a magnetic field, it's subject to a force, ILB, and the direction of that force is a result of right-hand rule number 1. And we know from the previous problem that the force is always going to oppose the motion. And so in order to slide at a constant speed, that force has to be, the applied force to make it move has to be equal to the force on the wire. And then in terms of power, the power output is the work you do, and the work, you've probably forgotten this equation from first semester, is force times distance, but the power is the work per unit time. And so the power equation, mechanical power, is force times velocity. And the electrical power, of course, is I times V, or any variation of it. So those are the equations you use. And by conservation of energy, those numbers should, in fact, be equal. Okay? Okay, I'm going to spend a few minutes explaining about the coil inside the coil apparatus. And this is the next the last three problems. So in each situation, you have a larger coil and a smaller coil placed inside it. And in each situation, the larger coil is the coil that's driven. So it's called the primary coil. It's the coil that has a source putting current through it. And when you put current through a coil, right-hand rule number 3, you get a field. So you can see the current comes in this way. It circulates, looking from above, it circulates counterclockwise, and the field is up. So the inner coil is inside the outer coil, and called the secondary coil. And in each case, what we're going to do is we're going to watch the output of this coil. So the first thing you want to realize is that, let me pause for a minute. Under normal circumstances, you would get to see a variety of real situations of this type in the diagram. So here's one. We actually have this in lab. Here's the outer coil. It has a very thin wire, so it actually has about 3,000 windings. And here's the inner coil, goes inside. The iron bar just makes this whole thing couple together better, but you don't need to worry about that in this case. And so this has a number of windings, which is different, and a diameter, which is different. And so when you put a current in the outer coil, that field fills the inner coil. And so if the field is steady, the flux is steady, and it's not changing, there'll be no response. So in other words, if there's no current in this coil, there'll be no response by this coil. But even if there is current in the coil and it's steady, this will be subject to a flux, but it's not changing, so there'll be no response. It's only when the current and the field, the current into this coil is changing so that the field is changing, right? And the field due to a coil, you know what that is. It's B coil equals mu naught I, N over L times I. And so only when this is changing will there be a response. So the three problems you're going to do, you're going to see three different kinds of changing input on the primary coil, and that will give you 3 different kinds of output on the secondary coil. Here's another similar arrangement that just stands vertically rather than horizontally. You would lower this in here. If you want it to work more efficiently, it does help to have an iron bar in there. But again, that's a detail that we needn't worry about right now. And finally, here's the exact apparatus that we use in lab. Here's the coil I just showed you. You can see a black and a red wire plugged into those terminals. That wire goes to here. This box is a multi-function box. It does a variety of things. And so this is the input. And the box, you can control different inputs like you're going to see in the 3 problems. And then here we read the output. So this, say, watches the voltage across this coil. So if the voltage and the current and the field and the flux in this is changing, then there'll be a non-zero output here. And the kind of output you get depends on the input, and that's what the 3 problems are all about. Okay, so in problem 10, the input, the voltage across the primary coil, generated by the box that you see, called a function generator, is going to be a cosine function. Looks like a sine function, but if it starts there, sine and cosine are the same curve, just where they start. This is a cosine function. And so the voltage is varying, just like it would in a any AC circuit, just like it would in household wiring. It varies between 2 maximum values. And since it has a repeating period, the length of time it takes to complete one cycle is called the period, and we use the symbol T. But if we sit at a point and watch how many waves go by each second, that's called the frequency. And so what you need to know is that the period and the frequency are reciprocals of each other. So we can write it that way. We can write frequency equals 1 over the period. And so if it takes a tenth of a second for one wave, that means there's 10 waves per second. Or if there are 10 waves per second, that means each wave takes a tenth of a second. So that's the relationship between period and frequency. And so when you see in the first problem the cosine function, it'll be 2 pi over t times the time. So you can see that 2 pi, that's radians. So when the time, the clock time, the little t, is equal to the period, you'll have completed one cycle. Let's say the period is 10 milliseconds. So when the clock reaches 10 milliseconds, you'll be at pi. When the clock reaches 5 milliseconds, you'll be at 1/2 pi, or a half a cycle. And when it reaches 20 milliseconds, it'll be at 4 pi. It will have completed another cycle. So that's how that function works, just so you understand that when you see it. But since the output is Faraday's law, we have to look at how the flux is changing as a function of time. And so there's some steps to be understood here. If I put an oscillating voltage, then the current that I get will simply be the voltage divided by the resistance. And so the current's going to oscillate in exactly the same way. Let me actually pull that function out. So this is the function of the voltage for problem 10. And so you can see that the cosine, as the time ticks off, it's going to go through a complete cycle every 16 milliseconds. And so if we were to graph this, let me pause and graph it. So this is what the graph would look like. Since the cosine varies, this term is going to vary from 1 to -1 back to 1, going through 0. And so when t equals 0, the cosine of 0 is 1. And so we start at 12.8 volts. And as the time goes by, after a quarter cycle, when t is equal to 4 milliseconds, this will be 1/4 of 2 pi, which is pi over 2, which is 90 degrees, which means it's 0. And then after 8 milliseconds, it will be here, 12, and then 16, it's completed a cycle. And then it's going to repeat every 16 seconds, keep repeating. So that's what this function does. And so this is the maximum value, as this varies between 1 and -1. So this is the input voltage here. And as this oscillates, it means that the current is going to oscillate, is going to follow it, because the current is simply the voltage divided by the resistance. And so if you divide this by the resistance, you'll get the maximum current. And that current is going to vary according to this very same graph. The period and the frequency is going to be the same, only the value will be the maximum current, which you get this way. Actually, I should write this: I max equals V max over R. But just like the voltage can take on any value, so can the current. And then from the current, you can get the field. So what's going to happen is the field is going to vary through here. And the field for a coil, we know, is mu naught N over L times I. And mu naught N over L are going to be constants given in the problem. And the I is just going to be this I. And so since the I varies according to this function, so too will a magnetic field follow the same oscillation, the same period, the same frequency. Only when you graph the magnetic field, these maximum values are going to be different. So this is how you'll get B max will be this times I max. But keep in mind, it's all varying over time, oscillating over time as a cosine function. So now what we want is we want to get the output. If we hook this up, if we hook the secondary coil up to a meter, which is what this does, and we watch the voltage, the output voltage, we're going to see that it varies also, because the flux is constantly changing. As the magnetic field in the outer coil changes, then the magnetic field passing through the inner coil is constantly changing, and there'll be an output. And the way you get the output is Faraday's law, no surprise. So the output is going to depend on the number of windings. That will be the number of windings on the inner coil. So be careful. When you calculate the magnetic field, you're going to be using the number of windings on the outer coil, because that's what's producing the field. But when you're watching the flux through the secondary coil, you need the number of windings on the secondary coil. And so you need to take the derivative of BA cosine theta. A is the area of the coil that we're calculating the induced EMF. Cosine, the field is always in the direction that the coil is facing, so this is 1. And so all you have to do is take the derivative of the B that you got down here on the input coil. That's what's going to be going through here. And so when you take the derivative of a cosine, you get a negative sign. But we're only worried about the magnitude, so you don't have to worry about the negative. But remember, when you take the derivative of a cosine, you have to deal with this constant that's in front of the variable. That's Calc 1. You can all do that. And that's, without going through the details, that's how you do number 10. So let me say a little more. I know this is going on forever. A little bit more about the instrumentation. Again, we're at this distinct disadvantage that you're not in lab and you're not seeing these things. But the thing that supplies the varying voltage to the primary coil is called a function generator or a signal generator. And the reason it's called that is because, unlike a battery that just puts out a straight, direct voltage that doesn't vary, a function generator can give you voltages like we just saw that oscillate sinusoidally or cosinusoidally, or in problem 11 you'll see that it gives you a voltage that oscillates this way. That's called a triangular wave or triangular function. And then there's another function which is a square wave, which you have a high voltage and then it drops quickly to a low voltage, and then it goes to a high voltage, stays steady, then it drops rapidly to a low voltage and stays steady. That's a square wave. And then you can combine the square wave with the triangular wave, where you get a rapidly changing voltage and then it falls off, and this is called a sawtooth. So there's all these different functions exist in a function generator, which could be a box by itself or it could just be part of this instrument. So this is the function generator, and by changing the settings you can pick any one of these functions. You can adjust the frequency or the period by adjusting a dial, and you can also adjust the maximum and minimum value. That's called the amplitude of the wave, right? Those are all adjusted by making adjustments to this box. But in order to see what's coming out here, right, you can't just put a voltmeter, because all you're going to see is numbers flashing all over the place as it changes. So you have to put a meter that can read and record voltages very rapidly and ideally plot them. And that is what's called an oscilloscope. It's an instrument that watches the voltage and graphs it as it's reading it. So like in problem 10, where the output is a sine wave, the oscilloscope would show that output, and it would show you the amplitude, and it would show you the period, and all that information you would get from the oscilloscope. And in the case of this box, it doesn't have a screen. So this box here that we actually have at HCC hooks up to a computer, and it plots the functions on the computer screen. Unfortunately, because we're remote, you're not going to get to see or experience any of this. Hopefully, when you take circuits, you'll get to do this in real. So in problem 11, the input, rather than being a smooth oscillating sine wave, is a triangular wave, or a voltage that changes from a negative value linearly to a positive value, then rapidly goes linearly to a negative value. And so that would be one cycle. That would be the period. And the minimum value would be this, and the maximum value would that, and it passes through 0 here. And so by using the maximum value of the voltage, you get the maximum value of the current and the maximum value of the field. And since the voltage does this, the current's going to do this, the field is going to do this. But when you want to find the output, that's Faraday's law. You got to take the derivative of this. So remember, the derivative is the slope. So this has a constant slope. It has a constant positive slope. And this has a constant negative slope. So the derivative between here and here is a constant value, which is the slope of this line. So that's a constant positive high value. And then when it switches here, it drops to a constant negative slope. and then it goes back to the positive slope, and then it goes back to the negative slope. So you see what you get for the output on the secondary coil is a square wave. And finally, in the last one, number 12, you connect the primary coil to a discharging capacitor, and we know how that goes. We know what the function is. And so this is just like problem 5 and 6. The voltage, current, and field through the primary, which is the same as what goes through the secondary, is going to start at its maximum value and decay to 0. And as we know from that problem, when you take the derivative of that exponential function, right, v equals v max e to the minus t over the time constant RC, a review of RC circuits, you're going to get the same behavior, the same time constant. But when you take the derivative, right, you got to deal with that constant inside the argument of the exponential. So make sure you do that right. Okay, I think we're done.